Here's a quick explanation of what a sampling distribution actually is, using StatKey to explain it. If you go in, search for StatKey, pull up the StatKey website, when you're doing a sampling distribution, they give you two options. You can either do it for a mean or you can do it for a proportion. Let me show you real quick on the mean how this works. The sampling distribution takes multiple samples from a population and creates either a histogram or a dot plot from there. So over here is some hypothetical population of values. What we want to do is create a sample of 10. So we'll generate one sample of 10. Down here, we pulled out 10 individual values from our original population. They're these. And we calculated the mean. Real quick, there's notation and there's some terminology that people get confused on. Up here, the mean 43.024 is from the population. It is called a parameter because it was calculated from the population. Its notation is mu. So mu is 43.024. It's that little weird looking U that has the tail on it. The standard deviation, because it's from the population, is also a parameter. Anything calculated from a population is called the parameter. The standard deviation, 29.259, is notated as sigma. It's the little one, little s in the Greek alphabet is an O with a horizontal line off the top. So mu sigma. In this sample, we have a mean for our sample data and a standard deviation for the same sample. These are not called parameters. If we calculated something using the sample data, it is called a statistic. The mean here is a statistic. It is notated as x with the horizontal bar. So x bar in this sample is 38.4, and the standard deviation for this sample is notated as little s. Little s is 34.578. What's happening is we take the sample and we look at the mean and we go and plot it over here. That was just one sample. Then we do this again. So let's get another sample of 10. There's our new sample of 10. So we gave back everything to the population, and now we randomly grabbed 10 more individuals to get these 10 data values. What is our new x bar? Well, the new x bar down here is 38.38. We go and we plot it. It shows up over here. Then we go back, return all those to the population, and generate a new sample. This sample of 10 has an x bar value of 45.7. We go and plot it. It's right here. That's our 45.7 value. What's going on is this. Every time we get a new sample, we're putting a new dot. The new dots get plotted here in what is called the sampling distribution. This graph we're making right here, this dot plot, is the sampling distribution. Up at the top, there's a couple of things that are happening. The top tells us how many individual samples we used so far. We made 22 samples and plotted all of their means. All 22 x bars got plotted here. The mean for this distribution, this is called our sampling distribution's mean. We don't have any notation for it. It's 39.6. And the standard error is 8.9. The standard error is the standard deviation, but it's the standard deviation for the sampling distribution. Now, we're all confused. Let me recap on what's going on. The population mean is mu. It is called the parameter. The population standard deviation is a parameter called sigma, the little s, the little O with the bar. Each sample that we generate has an x bar for its mean and an s for its standard deviation. Those are statistics. We plot each one of those inside of this dot plot, and we create what is called the sampling distribution. This distribution will have its own mean, and its own standard deviation, which gets called the standard error. If we generate a bunch of samples and keep plotting all their means, what starts to happen is the sampling distribution takes on this overall kind of symmetric, single-peaked, or we call it unimodal, some people call it bell-shaped shape. What we notice is when we do this for a large number of samples, I like to do this for 3,000 or 4,000 samples and plot all of them. When we do it for about 3,000 to 4,000 of them, we notice the mean for our sampling distribution is almost exactly the same as the mean from the population. What that tells us is this: we love taking a bunch of samples and plotting them out, because the mean for all of those samples that we plot will be almost that of the population. So even if we don't know what the population is, a bunch of samples generates a graph whose mean is almost the same as the populations. We could use it to estimate the populations. So that's why this is a useful tool. It's the same thing if you do it for proportions. So you can do some different things here if you'd like to play, but if you do it for proportions, they fix the proportion, and all you have to do is choose what sample size you'd like. What happens as you change sample size? Most of this stays the same. Let me show you the only difference that's going to really happen. We'll change this, maybe instead of a sample size of 10, let's do a sample size of 75. This time, as we generate an individual sample, we're getting 75 values down here, taken from the population. We get its mean, x bar, and we plot it. What happens if we do this a bunch of different times? Well, we'll still get the same overall shape. It still looks like a single peak, pretty much symmetric. And if you notice, down here, the mean of our sampling distribution is almost exactly the same as that of the population. They're very close in value. Both of them are 43 something. What has changed? The thing that has changed is the standard error. It got smaller. How do we know? What would it manifest itself as in this particular graph? Down here, the scale on the horizontal axis is narrower. So even though we got the same shape, it's over a much smaller set of values, range of values, than it was when n was equal to 10. So what do we like? We like big samples because they give us a narrower range that helps us approximate or estimate what we think the population's mean might be. Hope this helps give you an idea on how to use this for the mean. I'll try to post another quick video here on how you would do it using a proportion.